you hear me? Yes. Okay. So, of course, I start by thanking the organizers for doing a great job and for putting together this wonderful workshop. And of course, I thank them for inviting me to speak at MACO. So here's the title of my talk. This is a work I did with, I'm doing together with Daniel Vörös, who was a master's student at the time when we started. Now he's a PhD student, and Gergely Zarend at the Technical University of Budapest. Okay, so great. So let me start by introducing right away the model I will be looking at, which is a famous field theory in one dimension. It's called the sine-Gordon model. So for those of you who are not familiar with it, it describes a scalar field phi in 1D. So phi is a function of x and t, and this is the action. It's a relativistically invariant model, and the potential is cosine potential, which is maybe somewhat strange. So it's a periodic potential, and the sine-Gordon coupling is gamma. So G is not so important. It just sets some energy scale. The important coupling is gamma, actually. And why are we interested in this model? Actually, for many reasons, we like it. But maybe the most important thing is that it gives a low energy effective description of many 1D systems. So via bosonization. So if we have a 1D system, there are many systems in the Luttinger liquid universality class, but other systems have some gap opening perturbation, which make them gapped, and these systems almost universally are described by sine-Gordon model. So in bosonization, this cosine potential pops up. So for example, 1D fermions or spin chains, like the XXZ spin chain in an external field, or the Heisenberg spin chain with some dimerized coupling, they're both or all described by sine-Gordon field theory. Cold atom systems, like the ones studied in the lab of Jörg Schmid-Meyer in Vienna. Let me say a few words about this because this is very fascinating. They look at, I don't know if you can see it, there are two red cigar-shaped quasi 1D condensates that are coupled via tunneling. So atoms can tunnel between the two quasi-condensates. And this again, with bosonization, is described by sine-Gordon theory. Phi is just the relative phase of the two condensates in this case. And then they take, they use matter wave interference pictures to make measurements. And they can read out a lot of information from these interference pictures. You can see that see them at the bottom. Okay, and finally, I gave maybe a more recent example. It was recently proposed by Ananda Roy and Hubert Saleur that quantum circuits of Josephson junctions can also be described by sine-Gordon model. Okay, so let me tell you a few interesting things about this model. First, classically, okay. So it has a very interesting set of solutions called kinks or solitons. What they do is they interpolate between neighboring minima of this potential. So what happens is that at x minus infinity, the field phi sits in one of the minima of the cosine, which are at two integer multiples of 2 pi over gamma. At x plus infinity, it sits in another minimum, and energy density is concentrated only in the middle when there is this change, right? So it's a kink solution. It's a finite energy localized solution, and this is a static solution, but we can boost it up using relativistic invariance, and then it becomes a moving solution. So it's a non-dispersive wave packet, if you wish, made possible by the nonlinearity of the model. There is also something called the anti-soliton, which does the same in the opposite way. So it's decreasing. And actually, these were spotted in the experiments in Vienna. So in the middle interference picture, actually there is a soliton. Okay, and even more interestingly, oops, one can have multi-soliton solutions to the equations of motion. The theory is not linear, so I cannot just add two solutions to get a new one. So these solutions always describe the scatterings of these objects. So these are time-dependent solutions. This is a soliton anti-soliton picture, and interestingly, after the scattering, they regain their identities. These objects, they regain their shapes. Okay, and oops, was it me? Sorry. Okay, so clearly these objects are topological in nature, so we can define a topological charge to distinguish them. The topological charge is just given by the field value at infinity minus the field value at minus infinity, which means that the charge density is just given by the gradient of phi, dx phi, multiplied by this gamma over 2 pi to make it an integer. Okay. So soliton has topological charge 1, an anti-soliton has a topological charge -1, and for example, this configuration has topological charge 0. Okay, so this was classical. What happens? Let's see what happens in the quantum case. So actually, these interesting features that I've been talking about are possible because of the integrability of the model, and integrability is preserved in the quantum regime as well. In the quantized theory, these strange solitons become particles, maybe not so surprisingly, and they obey factorized scattering. Okay, what this means is that when they meet, not everything can happen. So if n particles come in, n particles will go out, and even the set of momenta is the same in the ingoing set and the incoming set and outgoing set. So you can say it's not so interesting, but if these particles have some internal degrees of freedom, which they do in the sine-Gordon model, this topological charge, well, that can have some non-trivial history in these scatterings. Okay, factorized means that we can break down all scattering processes into individual 2x2 scatterings using the symmetries of the model. So if we know the two-body scattering matrix describing these collisions, then we know essentially everything. Oops. And actually, it is known exactly. So it has this form. Interesting things happen when a soliton and an anti-soliton, so a plus and a minus, meet, because then two things can happen. They either go through each other. This is what I call transmission, or they can get reflected. These two processes are described by the amplitudes ST and SR. The probabilities are given by the squares. They sum to 1 clearly. Okay, and let me discuss two features. One interesting feature is that at a special value of the sine-Gordon coupling gamma, at 1/√2, the probability of reflection is identically 0 for all rapidities. This is because the sine-Gordon theory can be mapped to free fermions at this special value of the coupling. Okay, but outside of this very special point, there is transmission and reflection in general, but we can make another observation that at low incoming momenta or rapidities, it's the opposite actually. So transmission is suppressed, and collisions are dominantly reflective. Okay, so I will use this in a minute. And just for the experts, I'm looking at I'm focusing on this region of the regime of the coupling, so there are no breathers in my case. Okay, so now I've been talking about integrability, but of course real systems are never perfectly integrable. There are no infinitely many charges in the lab. Even more, even these nice systems like model systems, spin chains, XXZ plus staggered field and so on, these are not integrable either. There are always interpretive breaking terms. In the bosonization dictionary, there are terms that are neglected, there are cutoffs. And then it's a good question whether the integrability of the model helps or it may be an artifact in the description of real systems. So the goal is to describe somehow the universal behavior of generic systems, not necessarily integrable systems, in the sine-Gordon family. Okay, so what do I mean by sine-Gordon family? Well, the main features of the model are that there is a phase field, a periodic field, and there are associated topological excitations, kinks. These were these solitons, if you remember. And but I don't necessarily assume integrability. So this means that I cannot use the arsenal of integrability. I should use a less rigorous but more intuitive approach. And we didn't invent this approach. This was proposed by Subir Sachdev and collaborators. This is the so-called semi-classical approach. I will tell you about this in a minute. But it's time to tell you what I want to compute in this model. And mainly, I will be focusing on time-dependent correlation functions at finite temperature in this field theory of vertex operators. Okay, this is just a name for these exponential expressions. So for some reason, these are very natural objects in the theory. I mean, the potential itself is such a term, cosine gamma phi. Eta is just a parameter of these operators or observables. Okay. Other quantities I will derive from this. So let me quickly review this semi-classical approach, which was introduced in these papers. The idea is the following: if we are at low temperature and we have a gapped system, then we have a few particles, by which I mean there is a dilute gas of gapped excitations. So we are in the classical regime. They are far from each other typically, so they follow classical trajectories. You can think of this as a saddle point of some Keldysh path integral. So it's not completely rigorous. It's, as I said, it's intuitive to some extent. But of course, in 1D they will meet sooner or later. So I have to say something about the collisions. The idea is that we can compute expectation values by averaging over these semi-classical histories. Okay, so don't worry about these numbers. I will explain them in a minute. So, but these colored lines want to illustrate these semi-classical paths of particles. So time flows vertically. Okay, so these semi-classical configurations or histories are fixed by the initial state and the collision history. So let's see. First, the initial state. Well, the initial state is easy. I put particles uniformly in space because I have translational invariance in this case. I assign charges or internal degrees of freedom independently, and I assume some thermal velocity distribution for these particles. Okay. Now, what about the collisions? So first, note that multi-particle collisions can be neglected even outside of integrability because it's a very rare gas of particles. So the probability of 3 particles meeting is very low. Now, in the original papers listed at the bottom, people looked at the case when all collisions are perfectly reflective. Okay, as we saw in the sine-Gordon case, at low incoming momenta, collisions are almost perfectly reflective. And actually, there's an argument saying that this is the rule, a universal rule in gapped 1D systems. Okay, and this is somewhat, I mean, it's a big simplification because then the initial state fixes the whole history, right? Because the collisions are completely deterministic and classical. And in my talk, you will see I will try to improve on this aspect of the method. Oh, okay, so this is just a drawing of this perfectly reflective collisions. Now, I'm talking about the sine-Gordon model today, but so this slide is somewhat more general. So this approach was was not only applied to this sine-Gordon field theory, but to other models as well. Of course, then the particles are not solitons, but can be, depending on the model, they can be domain walls or spin flips or whatever. Okay, and of course, I have to tell you how to compute things. I told you that we have to average over these configurations, but still, we need to know how to compute observables. It naturally depends on the models and observables in question. Okay, so let me continue now with the sine-Gordon theory. I told you that I want to compute this correlation function, but if you think about it, in this semi-classical picture of trajectories, I put numbers. I promise I will explain them. So in most of the time, the field sits in one of the vacua of the theory, right? And these vacua were labeled by an integer, if you remember. These are the numbers in my drawing. But of course, when a soliton flies through the or passes, it changes the value of this, changes the vacuum by 1 unit. This is why you can see the numbers differ by 1 always, depending on, okay, it can be plus or minus 1 depending on the charge of the particle, of the soliton or anti-soliton. And what I have to compute for this correlation function is essentially the difference of numbers in the domains where the origin and x and t points are. Okay, and because this is just a field difference. Here, nu is a combination of the sine-Gordon coupling and eta, which is the parameter of my observable. Actually, almost everything will depend only on this combination. So, okay. So now, I will refer to this integer number as charge of the domain, because actually it's nothing else, but it can be computed from the charges of the particles that cross this green line. I don't know if you can see it, but there's a green dotted line connecting the 2 points in space-time where my operators are inserted. And clearly, if a soliton comes from the right, then it increases the charge of the domain by 1 and so on. Okay, so it makes sense to compute the probability of having KL left and KR right crossings. And okay, let me speed up here. So this is a very simple calculation of elementary geometry and probability. So this is a Poisson process because these trajectories are independent of each other. And the point in this calculation is that if we have perfect reflection, like the original method of Sajdev, or we have the free case, then there's a factorization in this average, because the charge average will only depend on this this number of solitons coming from the left or from the right. You will see what I mean by that in a minute. So let's continue with the simplest case, free particles. As you can see in the plot, particles don't do anything when they meet; they just fly through each other essentially. And then I can compute easily this charge part of the average, because each particle is either a soliton or an anti-soliton with 1/2 probability. So I get either e to I nu or e to minus I nu. And they are independent, so I get a product. I get a power of this expression, which is just cosine nu to the power of the total number of crossing solitons. And then if you plug these two ingredients into that formula on the top, you get a very simple series that you can sum up, and you get this exponential result. So it was all obtained by Sajdev and Damla in 2005. And the x and t dependence is not so trivial, actually. Even in this free case, you see the x and t dependence there. But if you look at autocorrelation function, so x is 0, or equal time correlation function when t is 0, then it's the result is really simple. It's just exponential decay in both directions. The decay rate is set by the mean collision time, essentially, and the correlation length is set by the inverse density, morally speaking. What about perfect reflections? So this is the universal quote unquote case of Sajdev and the original approach. Here, it's the situation is much more complicated because, as you can see, charges denoted by different colors follow zigzag trajectories. So they are not independent of the trajectories anymore. So it seems to be very complicated to compute this. But what helps is the following observation, is that the sequential order of the charges is invariant in time, which is, if you think about it, is almost trivial. Because of these perfectly reflective collisions, the charges of the domains don't change. And it means that if I can tell how much I shifted or how many domains I shifted to the left or to the right while I moved from 0, 0 to xt, then I can compute this average. Okay, this number of domains, the shift in the list of domains is given by the difference of right and left crossing particles. Because if a particle crosses from the right, I shift one to the right in the sequence of domains and so on. Okay, and then I can compute the expectation value at 0 time because it's invariant in time. And at 0 time, they are independent. So again, I get this cosine nu, but now it's raised to the power of not kr plus kl, but kr minus kl absolute value. And then, unfortunately, I cannot give you a simple final result. There are different representations for the result. It's not, the details are not so important. What is important for me now is that we can analyze the asymptotic behavior of this correlation function. And it turns out to be diffusive. So you have this e2 minus x squared over t over square root of t, typical diffusive form. Oops, sorry. The diffusion constant can be expressed again using the density and collision time. So this was the prediction of the original paper by Sajdev and Damle. But one can raise the question how universal this result is. Is this result robust in any way? If you think about it, transmissions are always present, even at very low temperatures. From time to time, there will be a collision for which there will be a transmissive process. We can even give an estimate for the time scale when this very rigid structure of domains changes. And then something will happen. So we try to improve the method by taking this into account somehow. And then it makes it more quantum and less classical. So Gergely likes to call it the semi-classical method for this reason. So the dynamics of these charges, and again, this is more general than sine-Gordon, can be captured in the following way. First, I can, and in this talk, I will use this method. I can decide at each collision, I can compute the amplitudes using the S matrix of the sine-Gordon model. I can compute the amplitudes of transmission and reflection. I can compute the probabilities by squaring them. And then I decide, based on these probabilities, whether there is a reflection or transmission. Okay. So by this, of course, I throw away some coherent processes or some interference effects, probably. It is a little bit like the Pauli master equation kind of thing in what one learns about the Boltzmann equation, for example, in the quantum case. These processes happen so rare that they can be considered to be essentially independent. Okay, but this makes the collision history stochastic. So this makes it much harder to compute things. We came up with another method which doesn't throw away these quantum superpositions. In this approach, we list the charges of these particles, building an effective spin chain. We can call it a spin chain if you wish. And whenever there is a collision given by the trajectories, we compute the S matrix based on the incoming momenta, and we act on the spins by the S matrix. So it's like a two qubit gate if you wish. And this we can do effectively using, for example, TBD or something like that, matrix product state technique. And by this, we really follow the quantum evolution of the internal degrees of freedom. But for today, in this talk, I will use this simpler stochastic approach. Let's see what we get. Sorry, okay, I wanted to mention these approaches have been used in quantum quenches and inhomogeneous transport situations in these papers. Okay. Now, before I show you some numerical results, let's see if we can make any progress in this setup. Okay, so I have the same semi-classical trajectory picture, but now if you notice that there are cases when there are transmissions, two of them at least, no, exactly two of them in this picture. How can I compute now analytically or semi-analytically anything? Well, we make some even cruder approximations. We assume, as I said, that transmissions happen randomly. Most of the time there are reflections. And the cruder, even cruder approximation is that we take the transmission probability to be a constant. So we forget about the momentum dependence of these amplitudes or probabilities. So there's a rate at which these transmissions happen. And why is this good? Because then we can map the problem to a famous classical problem, the simple symmetric exclusion process. So this describes hardcore particles that live on a lattice, and at a given rate, they try to jump to the left or to the right with equal probabilities, but no more than one particle can occupy a given site. This is the exclusion property. And in my mapping, soliton, let's say solitons correspond to particles and anti-solitons correspond to vacancies. Then when there's a transmission, they swap places, which means that there is a jump in this SEP system. Okay, of course, I have to make a translation between the time scales of the two systems. So there is real time, t, and there is SEP time, which I denoted by this hat, t hat, and there is a coefficient alpha. So it would be natural to take the average transmission probability, and actually that works for very low average probabilities, but transmission probabilities, but for a bit higher transmission probabilities, we realized it's better to leave it as a free parameter. So this will be the only one free parameter, and you will see how good agreement I can get with this one degree of freedom. So again, why is this useful? Because in a recent paper by Imamura, Malik, and Sasamoto, they derived exact results for exactly the quantity I'm interested in. Okay, not exactly, but it was easy to make the translation for any finite distance in the SEP problem and time in the SEP problem in terms of a Fredholm determinant. Again, the details are not important. I just wanted to advertise this beautiful result. And they gave the asymptotic behavior of this quantity. Interestingly, they found that if you scale distance and time in a diffusive way, so S over square root of t is fixed, then this quantity decays as E2 minus square root of t. So it's not exponential, but a stretched exponential. So now everything is ready to put together all these ingredients, making some saddle point approximation and whatnot. I get some prediction for my original sine-Gordon problem for the decay or for the asymptotic behavior, sorry, for this vertex operator correlation function. And this is what I get. So it's somewhat strange. It has this stretched exponential behavior times some power law, this t to minus 1/4. And I can put an intuitive picture behind this. So if you remember when we only had reflective collisions, then we got this diffusive result, because these domains were just performing Brownian motion essentially, or random walk. However, in the opposite case, when particles were free, then we get this exponential decay. And this is somewhat in between the two. So there is decay because these domains will change their charges, but the particles that make this change come from a region which doesn't scale linearly in time, but scales with square root of t. This is what we learned from the SEP mapping. Okay, so let's look at some data now. So in this plot, the small triangles or small dots are numerical semi-classical simulations, which means that we generated these initial states, we did the time evolution, we did the stochastic collisions, and measure this quantity many times. I don't know, I hope you can see there are some open circles. Maybe on the blue curve you can see them. This is not a simulation, but this is using this Fredholm determinant result, set result in the analytic formulas I showed you before. And you can see that the agreement is essentially perfect, even at relatively short times and even at relatively large transmission probabilities. I forgot to tell you that here the two curves at the top and the bottom are the analytic reflective and transmissive results, and we interpolated between the two by changing the changing gamma, the sine-Gordon coupling. Actually, then you can play with the average transmission probability. Okay, this is just a rescaled version of the same plot to show you that this time dependence. Oh, okay, sorry, this is the autocorrelation function. I forgot to say that as well. So x is 0 here. So the time dependence, this somewhat strange time dependence is checked in this plot. So the straight lines mean that, I mean, they provide good evidence that this is a correct, at least in the semi-classical picture, this is the correct asymptotics. And we also looked at finite x correlation function. Here we fixed the coupling and played with the temperature to move between the reflective and transmissive cases. And again, I think you can see that the agreement is very good. So this SEP seems to describe very well the processes. So you can ask at this point, wow, 3, okay. So you can ask at this point, what can I say about the charge density correlator? So what is the charge transport in this model? And I can compute that by differentiating, differentiating my vertex operator correlation function. You can convince yourself that this works. And what we found is that okay, just for completeness, for perfect transmission, so it's a free case, we get a ballistic result. So this 1/t dependence is a hallmark of ballistic transport. In the perfect reflective case, we get a diffusive result. Again, it's not so surprising. But what we find at weak transmission, so in this SEP regime, is that it still seems to be diffusive. So it's interesting that in this case, so in the perfectly reflective case, both the vertex operator and the charge density correlators are diffusive. But for weak transmissions, charge transport seems to be diffusive, but at the same time, the vertex operator already knows about these transmissions. So somehow it seems to be a more sensitive probe somehow. Okay, and I think I will quit. I will skip the last slide because I'm running out of time. Just let me give you one sentence about this, is that if you remember how I computed this correlation function, essentially that this can be regarded as the characteristic function of the transfer charge, the probability distribution of the integrated topological current. So we also looked at this, but let me just skip these 2 slides and let me come to my conclusions. So we try to describe the universal dynamics of generic models in the sine-Gordon family. And we found this stretched exponential decay of correlations for the vertex operator, and we found diffusive charge correlation functions, dynamical correlation functions. I didn't have time to talk about this, but the full counting statistics of the transfer charge, the moments of this distribution seem to scale non-uniformly, so depending on the power. And okay, so I told you several times that I'm not looking at the integrable case. Of course, in the integrable sine-Gordon, one expects the ballistic transport for the charges and an exponential decay for this vertex operator correlation function. So probably this, I mean, not probably, for sure, the stochastic assumption for the collisions break integrability. And in concrete applications, it's a good question which behavior will manifest itself. this one, that I just described, or maybe there will be signs of there are signs of the integrable dynamics. Maybe it's a matter of time scales as well. It's interesting to think about the intimate relation between the transport properties and the coherence of collision processes. And as an outlook, it would be very nice to compare these results with the generalized hydrodynamics framework, which is a hydrodynamics for integrable models, but integrability breaking terms can also be included. There have been a couple of papers already with this, so it would be nice to somehow make the connection with this more intuitive, but less rigorous and less controlled approach. So with this, I would like to thank you for your attention.
Thank you, Márton, for very interesting seminar.
Thanks for the talk. So in Kiron Malik's work with Sasamoto, there is a well, the initial conditions are very important, right? You have the quenched and annealed initial conditions which change the result for the exclusion process.
So actually, they looked at an even more general situation. They looked at this step-like initial profile.
Yes, this is the quenched.
Yeah, this is what you are referring to. Yeah, but for me, so I looked at now here at a homogeneous setup. But if you, this is a special case of their initial state. But you are right.
So another question is your square root of t, or at least in their work, comes from the diffusive scaling. So actually, it's just the system size which you blow up to infinity, right? This is
yes,
what they do. Yeah. So there are also results for finite segments. So you can there are different results, and then you have exponential which is proportional to time. So it's not the square root of t.
Okay. So what do? So maybe we should discuss it, because I didn't quite get the infinite versus finite comment.
We have another question here.
Yeah, thanks. This was very interesting talk. So the last part which you skipped was interesting for me, because you find these cumulants which don't scale as 1/t, right? Which you might expect from large deviation theory, right? So can you understand this? I mean, you could define scaled cumulant generating function, but the scaled cumulants would not exist, right? Because you have this t to the n/2. I mean, you understand?
So, yeah, you have a recent work on that.
Exactly. It is. Maybe we can discuss, but I just wonder whether I found immediate reflection on this.
Yes, so I didn't hear everything, but yes, I've been thinking of making the connection with your work, actually.
Okay, we should talk.
Yeah, that would be interesting, I think.
So I have one last question myself. So everything that you say seems to be independent from the sine-Gordon model, except for the exact form of the scattering matrix. Is that fundamental for the results, or is just a technical advantage?
So somehow maybe it was not crystal clear, because I jumped from general to sine-Gordon and back a little bit. So the method itself is more general than sine-Gordon, but I have to say that of course you have to adapt always things like, as I said, what are the particles, how you compute correlation functions. So it's not a completely universal method, of course. Some models are suitable, but not all the models. And for the concrete, if your question is about the concrete result, I think it's important that we have this kind of sine-Gordon family, which is maybe not a very well defined family of models, but more or less it's clear that you should have this stable topological kind of excitations and this periodic field. Yes.
Okay, so let's thank Márton again, and may Aldo approach.